Suppose t sub n of x is the nth degree Taylor polynomial for a particular function f of x centered at x equals a. Then we've seen that we can represent that polynomial in sigma notation. And in particular, if you look at the summation, which is that starting from 0 up and going up to k equals n, the terms are exactly the same as they are for a Taylor series. So we can actually think of a Taylor polynomial as a partial sum of the associated Taylor series. Because of that, we can now start to think about maybe using the polynomial to approximate the function. And as a result, anytime we have an approximation, we might be interested in the resulting error. One of the things we said about Taylor polynomials before is that when I have an approximation of f of x by the nth degree Taylor polynomial of f of x, then that approximation will improve if one of two things happens. If we either plug in x values that are closer to the center, or if we increase the degree of the polynomial n. And that second point was what motivated us to increase that to infinity in our getting a Taylor series. So in this lecture, what I'd like to consider is the idea of approximating a function by its Taylor polynomial, and then focusing on the resulting error, which we're going to call the remainder in this case. So we are going to define here that the remainder term, which again you can really think of as the error, is, we're going to refer to it as r sub n of x, and this is simply f of x minus the approximation of it, which is t sub n of x. So one important thing to notice, certainly with our notation here, is that the r sub n of x, this remainder term, it depends on n, hence the subscript there. So if I know the degree of the polynomial, then we're expecting that that should affect the remainder term. But of course, it also depends on x, what we're plugging into the function. And based off of our observations above, I should expect that when I increase n, or if I move x closer to a, then the remainder term should decrease. We should have a smaller error. So Taylor's theorem, or Taylor's remainder theorem, actually gives us a way to bound this resulting error or remainder term. So this, now I want to state the theorem, and it turns out the proof of this is pretty complex, but we will look at a very special case so that we get an idea of the connections being laid out here. So Taylor's remainder theorem, we're going to suppose that f of x is a function with n plus 1 derivatives. And by that I mean that it is a function such that we're able to take n plus 1 derivatives of that function. And I'm going to say such that the absolute value of the n plus first derivative of f is less than or equal to m for all values of x in some particular interval around the center. So for a general way of representing this, I'll say the interval, let's say from a minus d to a plus d. So d is measuring some kind of distance that we can move outward from that center point. So given this setup, we're going to say that for all x in that interval, we're going to be able to say that the absolute value of the remainder term is bounded above by m times the absolute value of x minus a raised to the n plus first power, all divided by n plus 1 factorial. So this inequality is going to be the key thing we want to remember about how we can bound our remainder term. Make this more clear. That's an n plus 1. So if we take a step back here, we can see the dependence now on both n and on x. Certainly n is coming through with the n plus 1 factorial in the denominator, as well as the n plus 1 exponent. And also, we can see that as I move my x value closer to a, x minus a is now going to shrink. So we can see that direct impact on our bound being smaller. So, and I'll also say that further than that, of course, this depends on our function f of x. That really comes in with m. So as I change my function f of x, some of these pieces are going to stay exactly the same, the x minus a to the n plus 1 and the n plus 1 factorial. But f of x is going to determine what this upper bound m is going to be. In another video, we're going to go through some direct applications of this to see how we could apply that, and I hope that will clear up kind of this idea of how one would find such an m. But for now, I want to come back to this statement, and let's just look at it in the very special case of n equals 1. So what does that mean? N equals 1, that's the degree of the Taylor polynomial. So all we're looking at here is the idea of approximating a function by its first degree Taylor polynomial, which you can also think about as its tangent line. So in the hypotheses here for this theorem, what we're going to assume is that the n plus first derivative, in this case that means the second derivative, in absolute value is known to be bounded above by some constant capital M. And for simplicity, I'm going to say in the interval from a to b, and I'll point out a couple things. You could interpret b here as a plus d to make it line up with what we have above. I just am going to find it simpler to write b on my integrals in a moment. And you'll notice also that I'm not looking at the left side of my interval, a minus d. This whole proof that we go through here, we could go through really a symmetric argument to look at the left side of the interval to also show that that would hold. So what does this mean? So if I have an upper bound on the absolute value of something, then thinking about what that means about what's inside of the absolute value, this really means that the second derivative is certainly bounded above by capital M, but it's also bounded below by negative capital M. Then let's think about how we can take bounds on a function and translate that to a statement of bounds on the integral. This is something we've actually encountered when we look at definite integrals before. So if I were to take the integral from a to x, and my assumption here is x is going to be inside this interval of interest, of the function f double prime of t. If I know that the integrand has this lower and upper bound, then that translates to being able to bound the integral above, where I replace the integrand with its bounds. So I'll put my negative out front here. So if we evaluate these integrals, then we're going to be able to say a few things. First of all, if I evaluate this middle integral, the antiderivative of the second derivative is the first derivative, and we're evaluating that from a to x. So that would leave me with f prime of x minus f prime of a. Then if I look at evaluating, let's say, the integral on the right there, that's going to just be the area of a rectangle with height capital M and width x minus a. And we have a similar idea with the negative of that. So we get this. The next thing I want to do at this stage is take the f prime of a and add that to all three parts of this inequality. And then that's going to yield the following statement. We're going to be able to say that f prime of a minus m times x minus a is less than or equal to f prime of a, or excuse me, f prime of x which is less than or equal to f prime of a plus m times x minus a. And it turns out we can do one more iteration of this, where now I have, in some sense, bounds on my first derivative of f. We started with bounds on the second derivative and then took those into integrating every part of that inequality. Let's do that one more time. So to carry this over, this tells me then that if I integrate the f prime of a minus m times t minus a from a to x, then it follows that that would be less than or equal to the integral from a to x of what's in the middle, the f, let me use a different variable here, f prime of t. And that is bounded above by the integral from a to x of f prime of a plus m times t minus a. So we can integrate one more time and again see what that leaves us with. So one thing we'll get on the left-hand side, we're integrating with respect to t and again evaluating our bounds. So this is going to leave us with an f prime of a, which is a constant. That would be times t, but evaluating that from a to x would leave me x minus a. And likewise, the next part of this would become a squared term. So that's going to be m over 2 times x minus a squared. Plugging in the lower bound of a would result in that part being 0. That's now less than or equal to the antiderivative of f prime is just f, and I'm evaluating that at the bounds. And then we get that that in turn is less than or equal to f prime of a times x minus a, now plus m over 2 times x minus a squared. So again, that's just evaluating the integrals above, and then the other part that I kind of lumped in is plugging in the appropriate bounds. So it turns out that this is all we really need to get us back to the statement from the remainder theorem. It's not obvious at the moment, but I can rearrange everything that I have, and what I mean by that is we can actually move this around and say that f of x, let's see, minus, right, so let's take, let me underline this. Let me take this part, which sits on both of these sides, and let's subtract that from all three things in the inequality. So if I do that, that's going to leave the minus m over 2 times x minus a quantity squared on the left side, and the positive version of that on the right side. And then I would have f of x minus f of a minus f prime of a, x minus a. It's this middle part that I really want to focus on. This is f of x minus f of a plus f prime of a times x minus a. So just distributing that negative sign. And what I hope that now looks familiar as is that this is actually exactly what we call t sub 1 of x. That is the first degree Taylor polynomial centered at a. Likewise, it is the way that we express the tangent line. So what I've really bounded now, both below and above, is the difference between f of x and its first degree Taylor polynomial. And again, that's significant if you think about our remainder term. So at this point, we have f of x minus t sub 1 of x is bounded below by negative m over 2 times x minus a squared, and above by positive m over 2 x minus a squared. And if I come back up to my definition of the remainder term here, this is exactly what r sub 1 of x is. So I'm making that observation. And the other thing to observe is that I have a lower bound and an upper bound that are related by a negative sign. So we can actually jump to say that not only do I have r sub 1 of x in the middle here in this inequality, but I can actually rewrite that as saying that the magnitude of this is bounded above by just the positive version of this bound. And what I'll come back to just to round this out is how does that compare to the remainder theorem, which is what I boxed here in red. So keep in mind, like I said, in this case, we were just looking at n equals 1. So if you think about putting in n equals 1 on both sides here, then n plus 1 is now 2. So I can think about this as 2 is the same thing as 2 factorial. And I should have, I've already seen a small mistake. I should have actually, well, no, actually I don't need it. I was going to say, because I have my absolute value, you can imagine here I'm squaring it, but I could put that absolute value in there. So technically, this is x minus a to the 1 plus 1, so squared power. And then we have m here. And so if you look back at my remainder term, we have exactly what we would expect if n were 1. And like I pointed out, there might be a little bit of haziness at this point in thinking about what m represents. But for this problem, we were assuming that we could find such an m. So it's the bound on the absolute value of the second derivative. When we go through some applications, I'll make a point of ensuring that we actually think about finding m and how we would do so. What does that represent with the given function?